Good day everyone and welcome. Today, we delve into the fascinating world of scientific language models with our paper, Galactica, a large language model for science. We explore how these models, like Galactica, can disrupt the traditional store and retrieve paradigm of accessing scientific knowledge, absorbing technical knowledge, and bridging the gap between scientific modalities and natural language. Stay tuned as we unravel the potential of language models in transforming our interaction with knowledge. Thank you. The traditional paradigm of accessing scientific knowledge has its limitations. It heavily relies on human effort for reasoning, combining, and organizing information, which creates a knowledge throughput bottleneck. However, language models are emerging as a new interface. They are strong absorbers of technical knowledge, including LaTeX equations and chemical reactions, and have the potential to disrupt the traditional store and retrieve paradigm. We've demonstrated the capabilities of these language models. They outperform tuned sparse and dense retrieval pipelines in citation prediction. They also achieve strong performance in knowledge-intensive question-answering tasks, particularly on mathematical, MMLU, and math benchmarks. This shows the potential of language models to revolutionize how we access and utilize scientific knowledge. Our research has made significant strides in bridging scientific modalities and natural language. We've seen that language models can learn tasks such as IUPAC naming through self-supervision. This opens up new possibilities for automating complex tasks. Furthermore, we've been able to formulate drug discovery tasks like those in MoleculeNet, using natural language prompts. This approach has shown strong results, even without direct fine-tuning. These advancements highlight the potential of language models in revolutionizing how we interact with scientific knowledge. Imagine you're trying to calculate the average of 43, 29, 51, and 13. You'd likely use your internal or external working memory to perform this task. This is a simple illustration of how humans process information, and it underscores the need for language models to evolve. They need an architectural change that supports adaptive computation, much like our own cognitive processes. Now let's consider how we traditionally access scientific knowledge. It's largely based on a store and retrieve paradigm. We store information, and then we retrieve it when needed. But this approach has its limitations. It requires a significant amount of human effort to reason, combine, and organize information. This creates a bottleneck in knowledge throughput, slowing down our ability to access and utilize the vast body of scientific knowledge available to us. This is the problem we're addressing. We're exploring how language models can disrupt this paradigm and create a more efficient interface for accessing knowledge. The figure on the right provides a visual representation of this concept. We're proposing a shift in how we access scientific knowledge. Instead of the traditional store and retrieve paradigm, we're looking at language models as a potential game changer. These models are not just repositories of information. They're dynamic tools that can absorb and process complex technical knowledge, such as LaTeX equations and chemical reactions. But it's not just about storing and retrieving information. We're exploring how these language models can be applied in practical ways. For instance, they've shown promise in citation prediction, outperforming existing methods. They've also demonstrated their effectiveness in knowledge-intensive question-answering tasks. Moreover, these models can act as a bridge between scientific modalities and natural language. This opens up exciting possibilities for how we interact with and utilize scientific knowledge. In essence, we're looking at a new interface for knowledge interaction, one that could potentially revolutionize how we access and use scientific information. We propose a new approach to accessing scientific knowledge, shifting from the traditional store and retrieve paradigm to using language models as a knowledge interface. These models have shown an impressive ability to absorb technical knowledge, including complex LaTeX equations and chemical reactions. In terms of performance, language models have demonstrated their potential by outperforming retrieval pipelines in citation prediction. They also show strong performance in knowledge-intensive question-answering tasks, composing a curated knowledge base to answer complex queries. Furthermore, these models have achieved high scores on mathematical benchmarks such as MMLU and math. This suggests that tasks traditionally considered human specialisms could potentially be solved using language model approaches. In summary, we believe that language models have the potential to revolutionize how we access and interact with scientific knowledge. Our research has shown that language models can act as a bridge between scientific modalities and natural language. For instance, they can learn tasks such as IUPAC, naming through self-supervision. They can also formulate drug discovery tasks using natural language prompts and even show potential for tasks like automatic protein annotation. However, there are still challenges to overcome. The availability of high-quality, step-by-step datasets is a current bottleneck. We also need to consider architectural changes to support adaptive computation in these models. Furthermore, as these models become more accurate, it's crucial to verify their generations for factual correctness. These are the directions we're exploring, and we're excited about the potential of language models to revolutionize the way we access and interact with scientific knowledge. Let's delve into the technical results of our study. The figure on your right illustrates Galactica's attention to functional groups, demonstrating its ability to use chemical knowledge in tasks like IUPAC naming. It focuses on relevant parts of the molecular graph, such as the nitrogen atom for amino and the sulfur atom for thiazole. Now, let's highlight some key results. Our language models have successfully absorbed technical knowledge, including LaTeX equations and chemical reactions. They have outperformed retrieval pipelines in citation prediction and shown strong performance in knowledge-intensive question-answering tasks. Through self-supervision, they've learned tasks like IUPAC naming. We've also formulated drug discovery tasks like MoleculeNet in natural language, achieving impressive results. These findings underscore the potential of Galactica in scientific and technical domains. In our research, we've delved into the potential of language models to revolutionize the traditional store and retrieve paradigm. We've found that these models are not just repositories of information, but powerful absorbers of technical knowledge, capable of understanding complex LaTeX equations and chemical reactions. Our findings also indicate that language models can outperform existing methods in tasks such as citation prediction and knowledge-intensive question answering. This suggests that they could become valuable tools for exploring scientific literature and knowledge in the future. Moreover, we've demonstrated the ability of language models to act as a bridge between scientific modalities and natural language. This opens up exciting possibilities for tasks like automatic protein annotation and drug discovery. As you can see in the figure, the distributional comparison of citations further underscores the potential of language models in the scientific domain. This is just the beginning, and we're excited to see where this journey takes us.